looking at small signal equations, small signal model for the induction machine in the last lecture. So, what we had was the expression for the machine equation was V equals R I plus L P I plus G 1 omega s into I plus G 2 into omega r into I. This equation being written for variables in the synchronous reference frame, and we have dropped the superscript and the subscript here in order to simplify the notations. We understand that it is in the synchronous reference frame. So, when you disturb the equations, we are let us review what we had done towards the end of the last lecture. So, if you disturb this, you have V naught at which the system was operating, and then you apply a disturbance which is delta V, that is then equal to this R into I plus delta I plus L I naught plus delta I, L into P of I naught plus delta I plus G 1 into omega s naught plus delta omega s into I naught plus delta I plus then G 2 into omega r naught plus delta omega r into I naught plus delta I. So, here the inputs, so to say, for the disturbances are delta V and delta omega s, because the frequency of the AC supply is also in our hands if you are looking at an induction machine controlled by an inverter. So, this equation consists of both steady state terms and the disturbances. The steady state terms must by themselves be equal on the left hand and the right hand side, and therefore, one can remove the effect of the steady state terms. This R I naught is, it can be removed. V naught is then equal to R I naught plus L P I naught plus G 1 omega s naught into I naught plus G 2 into omega r naught into I naught. So, these terms on the left and the right hand side, they are equal and hence can be removed from the equation, which then gives us an expression for delta V. Delta V is then R into delta I, that is from this term, plus L into P delta I, that comes from here. From this term you would have G 1 delta omega s into I naught, G 1 delta omega s into I naught, and then you will have G 1 omega s naught into delta I into delta I, and then you would have another term G 1 delta omega s into delta I, which we neglect in comparison with these two terms, because this is a product of two small disturbances which we consider it to be negligible. And then you have G 2 into omega r naught delta I plus G 2 into delta omega r into I naught. Similarly, we neglect the term G 2 into delta omega r into delta I. So, this is an expression that then relates the small signal inputs given as disturbances to the response, which is basically delta I and delta omega r. Apart from this, you have torque is equal to I transpose into G 2 into I, and therefore, in order to get the disturbed values, you could say T plus delta T equals I plus I naught, T naught plus delta T is I naught plus delta I transpose, into G2 into I naught plus delta I, and one can therefore write delta T as being, let us say, G3 into delta I. So, this expression would be dependent on delta I terms. So, we write it as some matrix G3 into delta I. So, this is one part of it, and then if you look at the mechanical equation, you have J d omega by dt equals this developed torque minus the load torque minus, let us say, some fluid friction, that is viscous friction, into omega, and therefore this can be written as J d by dt, or let us write it in the other notation, J into P of delta omega r. Note that this is omega r, that is the rotor speed, and this is also the rotor speed. Therefore, this is equal to delta T minus delta TL minus B into delta omega r. So, these are your equations relating disturbances. You have one equation here, and this is the mechanical equation, and then you have the electrical equation. This delta T is nothing but this expression which goes there, and therefore one can now combine all these three expressions and write it in the so called state variable notation, which is useful for further simplifications, and that can then be written as P vector delta I and delta omega. Note that this vector delta I itself is not a single element, it is a row, it is a it has 4 currents, 4 into 1 vector. If you neglect 0 sequence, otherwise it would be a 6 into 1 vector. So, this is then equal to L inverse multiplied by minus R minus G1 omega S naught minus G2 omega S naught, G2 omega R naught, and then in the second column you have minus L inverse G2 into I naught, and here you have G3 by J, and then here you have minus B by J. This matrix multiplied by delta I and omega r plus L inverse, and then minus L inverse G1 I naught, and then 0, 0, 0, 1 by J multiplied by delta V, delta omega S, and delta TL. So, this would then be the state variable representation of the small signal model. So, here you have the state vector, which can be written as P times x if you describe this as the state vector x, that is then equal to A times x, where this matrix is A and that is your state vector x, plus B times the input vector u. This is the input, this is B matrix, and then here you have the input vector. So, these are your inputs that are there, that is the change in the supply voltage, change in the supply frequency, and change in the load torque. Once you have it in this form, this is nothing but a series of differential equations, first order differential equations, and as we have seen in the case of DC machines, one can, if you want to solve this, transform this into the Laplace domain. So, you have S times the vector x of s equals a times x of s plus b times the input vector u of s, and therefore you can solve for x of s as s into identity matrix. Please note the change in notation here. It is usual to write in this expression s times I, whereas here we have used I for the vector of flow of amperes. So you have Si minus A inverse into x of s plus Si minus A inverse into b times u of s. That will then give you the state vector x. You can then take the inverse Laplace transform, and for any given input x, input u, you can find out what x is. That is what we have done in the case of DC machines and seen certain examples of what would be the response if you apply certain disturbances. Now that kind of an analysis can be done for the induction machine also. In this reference frame, the advantage is that all the variables here, that is I and V, they are basically DC. So as far as the equations are concerned and the way you use those equations are concerned, all these variables are DC, and therefore it sort of looks similar to a DC machine from that viewpoint. So this is small signal analysis. One can then go about deriving the relationships between, for example, delta omega r of s, how it is going to change with respect to, let us say, delta v d s. That means the stator d axis input, if you change that, what happens to delta omega r. So this is then described in terms of the Laplace variable s, and so you get some numerator by denominator both as a function of s. One can then look at the roots of the denominator in order to find out how this is going to change as with respect to time. As usual, the numerator function also gives you more information about the amplitude of the overshoot, etc. So one can do similar analysis as we had seen in the DC machine using this small signal representation. But this is not all. In the case of induction machines, in order to do closed loop control, it then becomes necessary to look at how to simplify these machine equations themselves. If you see, for example, in the case of induction machines, we have seen here this expression is the differential equation describing the electrical subsystem, and you basically have Pi here, which is what we expressed. The order of the equation itself, even if you neglect these terms, the order of the equation is you have 4 variables here, you have 1 variable here, so it is a 5th order differential equation, and therefore it becomes fairly involved in order to design your closed loop controllers for this arrangement. So one can then do something to simplify these equations a little more. So how does one go about doing that? That is what we will see now. In the machine equations that we have derived so far, what has happened is that you have the stator axis, this is your alpha stator axis, and then you have the beta stator axis, and we have transformed the equations to the synchronous reference frame, which means that you now have a reference frame which is, let us say, aligned at some angle. This is your d synchronous axis, and then you have the q synchronous axis. This angle is 90 degrees because all the axes are like that way, and then this angle is what we have called by the symbol delta, and we have said that d delta by dt is the speed at which this reference frame now rotates. For the synchronous reference frame, d delta by dt is nothing but the synchronous speed. So having said that, we have been seeing all along that you may have you initially had coils that were here. This was your stator coil and this is the rotor coil on the alpha axis in the stationary frame, and then you had the stator coil here and then the rotor coil here. What we have now done is transformed these things to have a stator coil on this synchronous frame and then a rotor coil on the synchronous frame. So you have a stator coil here and then a rotor coil here. If you look at the equations themselves, let us write the equation for the stator voltage V ds. So if you say that this is your stator, so plus, and V ds is applied here, and this is V ds, that is the rotor coil, and then V qs is applied here, and this is V qs, which is the rotor coil. Remember, S stands for synchronous speed and q stands for the axis, of course. As long as we write it below, it is a stator, as a superscript it is refers to the rotor. So Vds, if you take, that is a stator d axis, that we have seen is Rs plus Lss P multiplied by Ids, and then you have minus omega s Lss into Iqs, and then you have plus Lm P I ds minus Lm omega s I qs. This was the equation for the d axis voltage of the stator, neglecting zero sequence components. So this is neglecting zero sequence. Mostly that is true, zero sequence component does not flow in the case of an induction machine, because invariably the stator gets a 3 wire supply and zero sequence components are in phase, which means unless the neutral wire is there, there is no return path, and therefore zero sequence components cannot flow. This is what you therefore have, and if we look at this, one can see that this term is a di by dt term and this term is a di by dt term. It sort of looks like a d by dt of self inductance of the stator multiplied by the direct axis, the ds flow of current, plus a mutual inductance with the d flow of current in the rotor. If you have a system like this, you have one coil here and one coil here, and one were to write an expression for the flux linkage in this coil, let us say psi ds, how would you write it? The flux linkage in this stator coil arises due to a self flux linkage and a mutual flux linkage. There could also be in general flux linkages from other coils around, but in this particular case the other two coils are at an axis which is 90 degrees away, and therefore the flux component produced by this coils on this axis would be 0, and therefore if you want to write down the expression for flux linkage in the ds stator coil, you would then write it as Lss multiplied by Ids plus the mutual inductance, which is now Lm. If you look at this expression says mutual inductance between these two coils because we have now referred everything to the stator turns as well, in addition to referring to a common reference frame. This inductance, if you remember in the last lecture, we had derived this, so that is Lm into I ds. Similarly, one can write expressions for the other flux linkages as well. So, you have psi qs as LSS into IQS plus Lm into IQS. This is the flux linkage in the q axis coil of the stator is self inductance multiplied by the flow of q axis I, and then q current of the rotor multiplied by the mutual inductance. So, these are flux linkage of the stator. So, now this flux linkage of the stator, you see that there is one part which is along the d axis and this is along the q axis. So, which means having designated the axis here as d and q, the flux linkage of the stator has a certain d component, something here, and it has a certain q component which is something here, and therefore, the net flux linkage of the stator can now be drawn as a space phasor in this manner, where this length is then your psi ds and this length is your psi qs. Similarly, one can define psi ds, which is nothing but the rotor d axis flux linkage, that would then be the self inductance of the rotor LRR dash, because it has now been referred to the stator turns, multiplied by I ds dash, that is now the current flowing in the d axis coil of the rotor, plus Lm into I ds. So, this is the mutual inductance and the flow of current in the stator d axis. So, that is Lm into I ds. Together it then contributes the d axis component of the rotor flux linkage. We can write psi qs, which is the q axis component of the rotor flux linkage, as LRR dash multiplied by IQS dash plus Lm into IQS. So, now one can, just like we represented psi ds and psi qs as a space vector, this also has a d axis component and a q axis component. Therefore, this can also be represented as a space phasor. It could be some other space phasor, maybe like this. So, this is then your, this length would be psi ds and this length would be psi qs. Now, you see that you have 4 variables here, IDS, IQS of the stator, IDS, IQS of the rotor, and you have 4 variables here as well, psi ds, psi qs of the stator and psi ds, psi qs of the rotor. Therefore, one can, instead of describing this equation for VDS in terms of the variables I, one can choose to describe it as, instead of I, you can choose to have the independent variable as psi, or the dependent variable as psi. So, either what you could do is use these 4 expressions in order to eliminate all these variables IDS, IQS for the stator and the rotor, or you could choose to retain IDS and IQS of the stator, but replace these 2 variables in terms of these 2 variables, or you could retain these 2 and eliminate the stator ID and IQ and replace it in terms of stator psi d and psi q. One can therefore have many different ways of writing this expression. For example, let us say that we choose to eliminate the rotor d axis flow of current and the rotor q axis current, and instead replace this by psi ds and psi qs. How does one do that? What we will have to do? So, if we look at that expression, what you have is you can write I ds as psi ds minus Lm into I ds divided by Lrr dash. Similarly, you can write I qs as psi qs minus Lm into I qs divided by Lrr dash. I am not sure if that is really visible because of the older. Right. So, what one has to do is replace the variables for the rotor id and iq by these expressions, so that those variables are eliminated. So, let us look at the first equation again. You have Vds for the rotor is Rs plus Lssp into Ids, and then you have minus omega s Lss into Iqs, and then you have Lm p into Ids, that now becomes psi ds minus Lm into Ids by Lrr dash, and then you have minus omega s into Lm into Iqs. So, that now becomes psi qs minus Lm into Iqs divided by Lrr dash. So, in this way we have now eliminated these two variables Ids and Iqs. So, let us simplify this expression. So, what you have is you get one Ids term here, there is already an Ids here. So, what you have is Rs plus Lss p Ids, and then here you get minus Lm square by Lrr into Ids. So, it is Lss minus Lm square by Lrr dash p into Ids. So, this term has been taken care of, and then you have Iqs here. Similarly, you have Iqs here as well. So, you have minus omega s into Lss, and then here, so minus Lm square by Lrr dash into Iqs, and then you have plus Lm by Lrr dash p psi ds, and then here minus omega s Lm by Lrr dash into psi qs. So, we had an original equation, let us say Vds is this. We had the equation in terms of Id Iq of the stator and then Id Iq of the rotor. Now, we have eliminated Id Iq of the rotor using the definitions of flux linkages that we had written down, and now the expression is Id Iq of the stator, but psi d psi q for the rotor. Now, this can be done for all the equations, and when you do that, the resulting set of equations look like this. what you have is V ds, V qs, V ds, V qs. Zero sequence component has been neglected. These are the voltages applied to the stator DQ coils, these are voltages applied to the rotor DQ coils. The term S refers to synchronous reference frame. This is written as Rs plus sigma times LSSP and then omega S into sigma LSS, and this is minus RR LM by LRR dash 0 and then minus omega S sigma LSS Rs plus LSSP 0 minus RR LM by LRR dash LM by LRR dash into P minus LM by LRR dash into omega S RR by RR dash plus P, and this is omega S minus omega R, and then here you have minus LM by LRR dash into omega S dash P minus omega S minus omega R RR dash by LRR dash plus P multiplied by the current vector, that is IDS, IQS, psi ds, psi qs. So, this now becomes the voltage description of the voltage subsystem in the induction machine. There is also the expression for the generated electromagnetic torque, which then becomes Lm by LRR dash multiplied by IQS into psi ds minus IDS into psi qs. So, we have arrived at a slightly modified induction machine equation. We have replaced some variables in terms of some other variables. One might ask, what is the interesting aspect of this? Well, in this particular case, if you look at induction machine in general, normally the rotor is going to be shorted. So, VDS and VQS for the rotor are invariably 0 unless you are looking at induction machines fed from the rotor as well, a doubly fed kind of arrangement. Otherwise, these two are 0. Now, if you look at these equations, one can now try to do something else. That is, if you look at the figure here, we said that there is a stator flux vector and there is a rotor flux vector as well. Now, all these vectors, this reference frame is rotating at synchronous speed, and then this, the rotor flux vector is also rotating at synchronous speed, and then the stator flux vector is also rotating at synchronous speed. All of them are rotating at synchronous speed, and therefore, this angle under steady state, the angle that the flux vector makes with respect to the d axis, or the angle that the stator flux vector makes with respect to the d axis, is going to remain fixed. It is not going to change with respect to time, because all of them rotate at synchronous speed. However, this angle which the d axis makes with respect to the stator alpha s axis at t equal to 0 could be different. In other words, for the same stator flux vector and the rotor flux vector which are rotating at synchronous speed, I could have a d axis here, or I could choose to have a d axis here, or I could choose to have a d axis here, all of them rotating at synchronous speed of course. One can look at it more from the viewpoint of equation. You are saying d delta by dt is omega s, which means that delta is equal to omega s into time plus an arbitrary delta naught. How would you fix delta naught? Delta naught is the angle that the d axis is going to make with respect to the alpha s axis of the stator at t equal to 0. So one can now choose the d axis of the reference frame anywhere you want by choosing the angle delta appropriately, or in this case by choosing delta naught appropriately. And since you can now locate this reference frame anywhere you want, with the restriction of course that it is going to rotate at synchronous speed because it is a synchronous reference frame, I could choose this d axis the d axis of the reference frame along this vector psi of the rotor itself. I can choose this itself to be my ds reference frame. I can select it anywhere I want, here, here or wherever it is, but supposing I choose it here, then the q axis would lie at an angle 90 degrees to this, which means somewhere here, and this space phasor psi of the rotor would not have anything along this q axis, no part along the q axis, it entirely lies only along the d axis. So this is choosing a particular orientation for the reference frame, right. In order to do that, I would need to know by some means where this psi vector for the rotor is, and having located that vector, I now choose a d axis which lies along that vector itself. If we do that and we look at this expression for the generated electromagnetic torque T, you find that psi ds is nothing but psi of the rotor in the synchronous reference frame. Psi qs is 0. In other words, one could write the space phasor psi as being composed of psi ds plus j times psi qs, and if the reference frame is so aligned to be along the space vector psi itself, then psi qs becomes 0, and therefore this psi is just equal to psi ds. Of course this psi ds in general would be different. What we can see is, depending on where the d axis is located, the magnitude of the d component, magnitude of the q component is going to vary, which is what happens now if the reference frame is along this itself, q component becomes 0. So psi ds is then equal to the magnitude of the psi phasor itself, which means that now torque is nothing but Lm by Lrr dash into psi let me call it psi s into IQS. How is this interesting? If you look at the case of DC machines, let us draw that figure somewhere, maybe I will draw it here. In the case of DC machines, what we have is the field generated by the stator poles is there, and then you have the armature that is going to be rotating, and you place a brush which is in the magnetic neutral axis, and you have the armature conductors that are rotating here. Because the brush is placed in the magnetic neutral axis, the MMF produced by the armature, the field produced by the armature is oriented along that particular axis, and the field produced by the main stator field, that is the main field, is going to be oriented along this axis, which means that if you load the armature and the armature produces its own field, that field is not going to interfere with the main axis field, the magnitude of the main axis field under normal circumstances, because these two axes are separated by 90 degrees. No component of this will be present along this axis, which is a great advantage when you want to try and control the speed of the machine, or to be more specific, in order to control the generated electromagnetic torque. This torque is, if you remember back the DC machine equations, it was a mutual inductance multiplied by the field current multiplied by the armature current. That is true because the field current is producing a field in this direction, armature current is producing a field in that direction, and therefore if you want to control the generated TE, since it is proportional to IF and IA, you can control IA alone independently, and since IA does not influence the main field, you can keep this IF constant. As soon as you change IA, immediately it will reflect on the generated TE. In the case of induction machine, normally if you look at the 3-phase reference frame itself, this is not so. In the induction machine you have 3 currents. These 3 currents are responsible for the production of magnetic field inside the machine and also the generated electromagnetic torque TE. So, if you want to change the generated TE, if you change this current, it will result in changing the field as well as changing TE, and there is a big interaction that is going on. You will, unless both of them settle down, you will not be able to control TE really well. This approach, if you now look at the induction machine in the synchronous reference frame, you are able to identify which component of the flow of current in the stator is able to affect the generated torque, and if you choose your reference frame appropriately, in that reference frame one can see that the generated torque is simply a product of the rotor flux vector multiplied by the stator q axis current, and therefore if you can maintain the rotor flux vector independently stable at a fixed value, then as soon as you change q axis I, that is IQS, it will immediately reflect in a change in the generated electromagnetic torque. This is to say that this expression means that we are now by transforming to the synchronous reference frame with the d axis aligned along the rotor flux vector, we are looking at an induction machine which behaves essentially like that of a DC machine, and therefore in this reference frame the machine should be much easier to do closed loop control. One can look at these expressions further, and one can see that from these machine equations which we have written, from the equations that we have here, one can look at these two equations and it can be simplified. What you have is VQS, which is nothing but 0, that is equal to RR into LM by LRR dash into IQS IDS, and then VDS, which is again 0 because the rotor is shorted, is minus RR LM RR dash, that is, by LM LRR dash into IDS plus RR by LRR dash plus P into psi ds. So, if you look at this equation, one can recast this equation to say that psi ds is nothing but RR dash LM by LRR dash into 1 by P plus RR dash by LRR dash into IDS. In terms of the Laplace variables, one can then call this by the Laplace transform of IDS as a function of S. This P can be written as S as the Laplace variable. Now you see that the flux vector psi ds, if you orient it along the reference frame, psi ds is nothing but the rotor flux vector psi s itself, that is just straight away dependent on IDS. If you control IDS, you determine what psi s is. This is related only as a simple first order equation, which is again similar to that of the field in the DC machine. So, we can say that IDS controls the flux in the machine, whereas IQS determines straight away the generated electromagnetic torque TE. And one can get from this equation, if these two are met, then this expression gives an idea of the slip in the machine. This says that omega s minus omega r should then be equal to RR dash LM by LRR dash into IQS by psi ds. Right. So, this in turn is nothing but the slip. So, if you have a machine where you can directly control or where you can directly give as an input IDS and IQS, these equations say in this particular reference frame, when you are viewing the machine, it should be feasible to control the induction machine just like you control a DC machine. So, incidentally, then this forms the basis of what is called as field oriented control of induction machines. Field oriented control, sometimes it is called as vector control of induction machines, and here the orientation is done along the rotor field vector, and therefore this is called as rotor field orientation. One can derive other forms of expression where you can do a stator field orientation or magnetizing flux vector orientation. There are so many different ways in which these have been described in the literature. So, this is again one of the other useful aspects of looking at models of the induction machine in various reference frames. These are all in the synchronous reference frame, but we have replaced some elements, some unknowns or dependent variables by certain other dependent variables. You can, for example, choose to, as I said, retain IDS IQS here, but then convert these two to psi ds and psi QS of the stator, derive more equations, and then try to look at machine description in that. I would urge you to look at the literature for other ways of describing this and other ways of field oriented control that this sort of a description makes feasible. So, we have looked at induction machines over the last several lectures, and then seen how this ideas of machine modeling have made feasible different ways of analyzing the induction machine. Small signal analysis kind of thing is feasible because of this kind of a representation. There is much more in the literature, and I would urge you to look at literature for more elaborate arrangements. From the next lecture we will start looking at models for the synchronous machine and see how they can be represented and analyzed. We will stop here with this lecture.